In pre-modern medicine, diseases have a magnitude, which means that they have a duration in time and a spatial extension as they affect either the body as a whole or certain parts thereof. The possibility of conceptualizing morbid conditions in relation to their duration in time lies at the core of an old Hippocratic distinction between chronic and acute diseases, with acute diseases characterized by a shorter duration but more intense pain. Yet the origin of the tradition associating disease with a magnitude is usually ascribed to Galen. After offering a brief sketch of Galen's ideas, in this lecture, I shall focus on the latest developments of the Galenic tradition from the 14th to the early 17th century, and will consider how the concept that diseases have an intensity developed, and how these developments reverberated on the invention of early modern precision instruments. I shall begin with some preliminary remarks on the concept of intensity. Today, we define intensity as the distribution of the number of events per unit of time. This definition is sufficiently general and intuitive to apply to a variety of phenomena: light, sound, color variations, odors, and even perception, and some say mental states. This way of conceptualizing intensity is the offspring of the Middle Ages and developed conjunctly across the fields of medicine, theology, and natural philosophy. From the mid of the 13th century, words such as intensio and latitudo were used to explain the variation of phenomena in time, not only those described above, but also abstract concepts such as charity, purity, goodness, and similar. Medieval philosophers, and most notably a group called calculatores, conceptualize intensity as the addition of parts of a given property, say hotness or coldness, in a material medium, with the result that the addition or subtraction of such parts rendered the object hotter or colder. Yet these philosophers did not come with this idea out of the blue. They were reworking and reshaping a medical intuition originating with Galen and systematically applied by his followers. Galen of Pergamon had felt the need to approach diseases not only functionally, as to their hindering the normal bodily functions, but also quantitatively, in terms of when exactly they started doing so and how much they did so. To describe this latter aspect of his quest for quantity, he adopted two different terms. The first one was megatos, which features especially in the Methodo Medendi to refer to the greatness of a disease. The second one, which crops up most prominently in the Ars Medica, is platos, or range, latitudo in Latin, which denotes the intensity of a given condition. This intensity coincides with the progressive deterioration of health, which vary from subject to subject and in relation to environmental factors, such as seasonal changes and geographical conditions. Galen notes that the same disease can thus manifest in different degrees, and that is therefore associable with an interval or range. He conceptualizes the gradual change from one state to the other as a motion towards either the restoration or the progressive deterioration of health. As a continuous change, the deterioration of health was supposed to take place via an intermediary stage called udeteron or neutralitas, usually identified as the condition of convalescent patients. Therefore, not only disease and neutrality had a range, but also health, which acquired a new, more precarious meaning. Human health, in particular, started to be regarded as a condition constantly oscillating around an ideal equilibrium, which the Latin called equale ad pondus, the exact equality, which could never be fully clenched. And yet, despite the use of suggestive terminology, which seems to imply an interest in quantification, Galen's range and magnitude, megatos and platos, are not purely quantitative concepts. Galen is mostly preoccupied with the extent to which normal functions are impaired by the progression of a given disease in the body. Hence, the range of health, neutrality, and disease do not point to the duration in time of a certain condition, but to the stage at which the symptoms of a latent disease manifested themselves more clearly. The range of each condition stands as a qualitatively different state whereby time, as a quantitative parameter, is implied only tangentially. For instance, Galen refers to patients as being healthy or sick simply, simpliciter, presently, ut nunc, or most of the time, ut plurimum. And while it's clear that the latter two conditions, presently and most of the time, have a direct bearing on their duration in time, the former one, simpliciter, simply, remained quite a quandary to many of his followers. In fact, it could be translated as either absolutely or for all the time. The task of solving Galen's puzzles and turning his classification into temporal ranges was the task of the Italian physicians of the Middle Ages. These physicians fundamentally reworked Galen's rationale in two important ways. Firstly, they turned the term simpliciter into a purely temporal concept that referred to the persistence of a condition for all the time, semper. This task was undertaken especially by Gentile da Foligno, 1280-1348, and was called by his followers via gentilis or gentilis method. Secondly, they specialized and visualized the range as a linear distance from the point of the perfect equilibrium. This point of equilibrium, coinciding with the perfect health, was considered a mathematical abstraction in that, as seen, no human or living being could ever be said to stay in that condition. It was nonetheless necessary to pose such a point to visually define the space pertaining to the three ranges. By doing so, Galen's qualitative ranges, the three latitudines, became different regions of the same line, which encompassed health, neutrality, and disease. Now, Galen speaks of the latitude as one line divided in three. The point with this division, this Galen uses qualification for that are not purely extensive, they are not purely quantitative, sorry. So time seems to be implied, but only to a certain extent. It is noteworthy that this visualization made it also possible to turn intensity into a pure geometrical concept, progressing from a minimum to a maximum degree. The greater the distance from the perfect health, the more intense, severe the condition of the patient was. Visually, this new approach had a variety of outcomes. For the sake of clarity and brevity, I will here illustrate only three of them. Those modeled on the planetary spheres of the Aristotelian cosmos, those hinging on the classification of mixtures and substances, and those representing health and disease as pyramids of intensity. It is relevant to note that these efforts to visualize intensity gained momentum in the 16th century, when the works of medieval masters such as Gentile, Turisanus, Jacopo della Torre, and others became available in print. Medieval manuscripts are only seldom provided with diagrams. It is interesting the visual rendering of medieval theories goes hand in hand with the new geographical and astronomical discoveries, which made the necessity of mapping the regions of the cosmos and the geographical latitudes of the Earth more crucial. So the first group of diagrams I shall discuss here belong the diagram of Pietro d'Abano, 1257-1316, which, progressing from the center to the periphery, classifies all the complexions pertaining to health and then to animals and vegetables, as these lie outside the normal parameter of what is human, and thus associable with, they are therefore associable with primordial and more extreme states of being. To the second group of diagrams, we can ascribe Gentile's model of intensity, in which all possible substances and their complexion are classified in a progressive order from the minimum to the maximum range. Now, probably here some explanation is needed. I marked with a starker color the point of perfect equality between the four conditions: dry, wet, hot, and cold. Above that line, you have the range of hot mixtures. That is the only one that we can basically perceive, because everything that exists as a living or natural being has some part of heat in it. So below that line, nothing is possible. But above that line, Gentile is keen on classifying metals and then vegetables and then animals up to the highest degree. Okay, this classification, I should also point out in passing, is also a classification of the perfection of these beings. Okay, the perfection is the capacity of these beings to remain within a range that is allocated to them, allotted to them in the order of beings. The latter model I will illustrate is one of the latest and the most advanced. It belongs to Benedetto Vittori's Theorica Latitudinum 1556 and portrays the point of perfect equilibrium as the peak of a pyramid of intensity, pursuant to the idea that any condition receding from the perfect health represents a fall, lapsus, towards sickness. So at the center you have the perfect balance, which is also the discrimen, what the ancient called the crisis. Before and after that, you can only have what is less than that, okay? That the discriminating point, the perfect equality, which exists only as a mathematical abstraction. This term, lapsus, you see I marked it lapsus per calidum and lapsus per frigidum, introduces us to the standard designation of intensity in practical medicine, according to which conditions were falling in rapport to the hot or cold range. So they spoke of a complexio lapsa per calidum or a complexio lapsa per frigidum. Looking at these diagrams that suggest an implicit use of quantification, one might rightly wonder whether their use led to any actual measurement. The short answer to this would be no, it did not. The reason for this apparent failure is that the various schemes and diagrams used by medieval physicians to measure the range of health and disease all suffer from one and the same problem. They set the intensity of morbid conditions by deducing them from the point of perfect equilibrium, which, not existing and not being proper of any individual, distorted all the possible correspondences that could be drawn between the actual line of the diagram and the duration of disease in time. To establish a direct connection, instruments needed to be invented and then applied to everyday practice. As I've shown recently, their invention partly hinged on medieval conceptions of intensity and partly on new ideas on the structure of matter, now seen as corpuscular. The key figure in this development was the Venetian physician Santorio Santori, a colleague of Galileo who predated his inventions and corpuscular theories of some 30 years. Santorio is a Galenist with a penchant for experimentation and a bunch of new ideas in mind. He realizes that the major difficulty in converting Galen's ideas into practice is the divide between the demands of medical theory and the condition of the patients. He knows that this divide is the cause of the uncertainty medicine has fallen prey of and the recent triumph of empiricism, which he finds not only vulgar, but also evil, in that empirical doctors kill people. In seeking a way out of these impasses, he reworks Galen diagnostic rationale in three essential ways. The first is methodological, the second one is theoretical, and the third is experimental. As for method, Santoro opposes any theory claiming that individuals, meaning by this not only an individual human being, but anything claiming individual ontological status, exist per se. He claims, in this being ahead of Galileo, that our mind is unable to grasp anything individual, for it can only dwell upon the complexion of universal properties, whose complex arrangement determines the individual variations we recognize in medical practice. As a consequence, individuals cannot claim any ontological priority on universal properties, which are accordingly present in all of them and in the same way. They only differ in the fact that in an individual being, say me, they are instantiated in a particular time and space. The consequence of this turn is that, being universal, these properties are homogeneous in kind and can thus be counted. The second move Santoro makes is even bolder, for he claims that the fundamental structure of matter is corpuscular and that the basic properties of it are geometrical: number, figure, and position. Complex properties emerge from simple ones by way of complication, as in the clockwork, where the position of gears and springs make it possible for the clockwork to work the way it does. And everyone will have now, at this point, Descartes in mind, and this idea that the world is a clockwork. As a result of this conceptual molding, Santoro is now able to translate the universal properties instantiated in individual beings into exact quantities, and he invents instruments that measure it. First comes the pulsilogium, an instrument that measures the variations in the frequency of the pulse by using a pendulum. I usually locate the invention of this in 1590 because he uses this instrument in pair with his weighing chair. Then comes the thermometer, or hydrolabium sanctori, which was invented approximately 1610. Attention, because this is already a thermometer, is not a thermoscope. It gives you the temperature of a person or an environmental condition. Then comes hygrometers, which use impregnable substances, and the change in the structure and texture of these impregnable substances results in the change in length of the material that can be tracked. And finally, the most famous of all instruments, Santoro's weighing chair, called also statera medica or sella sanctori. This is famous because, of course, Santoro is being called the first self-experimenter in history and the one who originated the importance of weighing experiments in the history of medicine and science. All of these instruments embody the Galenic principle that the longer the distance from the point of equilibrium in the body, the more intense the disease is. To find this point, which, as seen, had managed to remain a purely mathematical abstraction to his predecessors, Santoro spends 30 years of his life painstakingly measuring his own weight, pulse, temperature, and the way in which environmental circumstances help or hinder the restoration of the bodily balance. The main assumption substantiating Santoro's measurements was that an organism has the capacity to adjust to external solicitations and resist the onset of a disease. This is, as a technical wording in Latin, it's called the potentiality to resist decay, potentia resistendi aegretudinis causis. Over time, therefore, the parameters granting the body healthy state are kept as close as possible to invariability if the body is healthy, which means the same weight, the same pulse, and the same temperature. Yet, Santorio also knows that these parameters are not perfectly constant, but that the way organisms react to external, that is to say, environmental or internal, namely pathological changes, vary from one individual to another and within the same individual. Health oscillates around the point of equilibrium and has a latitude, as Galen had taught his pupils. Santorio concludes that if we want to find when and how much a person is diseased, we must know what the parameters of the healthy conditions are, so that we can gain by difference the greatness and severity of the disease, what he called the magnitudo morbi. So we are back to the question that we posed at the beginning. What is the magnitude of the disease? The magnitude of the disease is the range within which you are healthy. I have to measure it, Santorio says. He spends much time pointing out all the continuities with Galen, and especially in his commentary to Galen's Ars Medica, he presents his instruments as ways to measure how severe is a morbid condition by measuring the distance, the recessus, from the normal healthy state. To understand how Santorio used these instruments, we have to follow closely what he states in the passages of his commentaries on Galen and Avicenna, 1612, 1625, 1626. In a passage of the third part of his commentary to Galen's Ars Medica, Santorio provides us with a rare insight into his methods. Instruments like thermometers, pulsimeters, and hygrometers, possibly even a rudimental form of weighing chair, are brought to the patient's bedside to define whether he is healthy or sick with regards to a pre-established parameter that Santorio has already observed on himself. These enabled instruments to measure, by difference, how severe the conditions of the patient were. For instance, as admitting that Santorio's thermometer had a resolution of 10 degrees, and that a degree around 6 was the temperature proper to the majority of healthy persons, a temperature of 3 or 9 in a patient could shed light on the severity of the patient's condition. By locating the individual condition over a range that can now be measured, these instruments provided a quantitative estimate of the patient's condition. Sorry, it's difficult to grasp. Of the patient's health, which was infinitely more precise than anyone could gather by interpreting the symptoms of a given syndrome according to the standard Galenic rationale. The results obtained by scales, pulsimeters, thermometers, and hygrometers are primarily comparative and yield the difference between pairs of measurements expressed in degrees. In short, they are intensity meters. They offer a solution to a medical problem that is at once diagnostic, to find out when a patient starts being diseased, and practical, how much the physician should intervene on the disease with drugs and other remedies. As seen, the intensity range is conceptualized in terms of segment length, so that the more the conditions of a certain body verge towards the extremes, the more they intersect one or the other extreme of the segment. The operationalization of this concept is evident in the case of these instruments. The indication they provide, in fact, is read by means of a graded bar of either linear or circular shape, to fast to slow a pulse, to high to low a temperature, to dry to wet a weather condition will be, the more it will approach one or the other extreme of the graded segment. The question is slightly more complicated to grasp in the case of scales. Let us assume as an example the motion of an equal arm scale deflected from its point of equilibrium. The essential aspect to bear in mind in this case is that as its movements are projected on a linear plane, this scale will produce segments that are shorter in proportion to the intensity of the force applied to deviate it from the point of equilibrium. Hence, the result is the reverse of that which we would expect. Yet, it is relevant that Santorio performed these medical trials not on equal arm scale, but on a stellar scale. In the stelia, the point of equilibrium is the centered, and so one arm is longer than the other. Projected over a linear plane, its motion will produce segments that are longer in proportion to the force needed to restore equilibrium, with the weight on the longer arm moving progressively to the end of it. As an example, if a body that weighed 80 kilos gains 5 kilos without committing any excess in normal habit, then the condition of this person has worsened. As Santoro is mostly interested in the retention of perspirable matter, this particular matter is constantly evacuated by the body but is not seen, and he associates an abnormal increase in weight with the onset of a latent disease, it is clear that also in this case, greater segments correspond to an increase in weight and thus to a more severe condition. Nearing the conclusion of my talk, I promise new sources on the invention of early modern precision instruments, and I am ready to deliver on that promise. One of the fundamental questions that has managed to remain unaddressed for centuries was, in fact, what did Santoro's instruments look like? He displays some engravings of them, which I've shown, but how big and handleable they were, what patients they were used on, how often and why, has remained a puzzle to historians thus far. Santoro promised to reveal these details, but managed to die before published a book on medical instruments never seen, that he promised many times in his published writings. Well, I think I have found an early source that not only shows that the book in question existed, but also sheds some light on the riddles historians have faced with regards to the invention of these instruments. This source, which I will not disclose as I'm currently preparing a paper on it, dates 1620 and is from one of Santoro's pupils, although not one very grateful to his teacher, as he only mentions Santoro's name once in a marginal note. The pictures you see refer to thermometers. The text provides fundamental information as to what the instruments measure, their dimensions, usage, and the characteristics of the experimental sample. For instance, we gather that Santoro's patients were predominantly nobles, insofar as their perfect health was paramount to the functioning of the Venetian Republic. Santoro is clear that these instruments allow maximal precision. So for everyday diagnosis, you could still rely on Galen's rationale. What you want to achieve with these instruments is absolute precision. You want to know ahead of time when a particular disease is introducing in the body. Since the most fundamental properties of a living being are geometrical or quantitative for Santoro, these instruments allow you to predate, prevent, to come before the onset of disease. Something I haven't said, but I hope it will pop up during the question time, is that one problem implicit in Galenic diagnosis is that the progression from health to disease is insensible. You cannot notice that. You can only notice when a vital function is impaired. It is already too late. Santoro wants to come before that. So these instruments allow you to sketch out in advance whether the body is regressing from the normal state and therefore progressing towards disease or not. And these he applied especially to those who he thought were those who most needed it, and therefore nobles. Another important aspect that emerges from my discovery is the practical application these instruments allowed, especially thermometers to measure the temperature of the air. These indications were used to warm up or cool down a room so that the patient's body was prevented from exposure to extreme environmental alterations. The Stelia chair served a similar purpose in that it helped to establish how much food and drugs should be taken as a consequence of the organism receding from its normal parameters. And the source specifies that for people who find weighing themselves strange or awkward, there are alternative practices available. One of these was an early and somewhat portable device consisting of a stone over a bench to counterbalance the weight of a person. While certainly cruder an instrument than Santorio's weighing chair, such a device would have the advantage of being readily available in place. This new testimony provides us with first-hand evidence that the new instruments were used not just in natural philosophy, but to concretely intervene on the patient's health and to quantify therapy, yet in a way that was consistent with a long medical quest to define and measure the intensity of diseases. With this proviso in mind, I can finally come back to the main question of this talk, namely the development of the concept of intensity and its relevance in the making of early modern science and the invention of precision instruments. Measurement and quantification have always, and rightly, been considered instrumental to establish the character of an experimental science. Yet, for a long time, medicine has been excluded from the consideration it deserves in shaping the emergence of experimental philosophy, as its contributions were seen as derivative of those in physics and astronomy. Yet, for all the discontinuities that mark the emergence of the new science, fundamental continuities are clearly present, motivating a critical but not dismissive approach to the past. And this was the case of medicine. The history of scientific progress that emerged from my research is one that refuses great narratives of discontinuity and acknowledges instead local or selective continuities. The works of authors like Santorio, but the same would certainly apply to Harvey, Beckmann, Sennett, and Leibniz, whose contributions have been instrumental to the emergence of early modern science, prove that they were constantly drawing inspiration from the past and were seeking new ways to deal with ancient problems. As a result of this, the Kuhnian paradigm shift, namely the assumption that scientific progress is achieved by sudden and radical changes in the background assumptions, is too one-directional to apply to the case we witness here. The past, which should have never survived, and I'm referring specifically to the legacies of Aristotle and Galen, refuses to fade away. Silently, this past keeps shaping the directions of science, reminding us that to be successful, even revolutions must take place within larger continuities. Thank you very much.